All right, so I had not hit go live. So let's see here. All right. Can you hear me now? Mo, no. Yes, no. All right, so Jacob can see and hear me. There we go. All right. Yay, okay. So, all right, so how's the audio? We are live, excellent. Okay, so you can thank my kids who are using or are aware of gaming. So they are the ones who told me about this streaming, and some other people. I want to test another thing here. I want to make sure my webcam is working, and then I think we'll go ahead and get started. So let's see here. All right, so can you guys see my webcam? Crisp, good audio. Audio is good, good. Okay, how about webcam? Can you see my webcam? Excellent. Okay. Thanks, Hal. Appreciate that. All right. So I'm not sure if this is the best format for us to use for the class, but I'm sure you guys will help me figure out what you think works best for you. So I'm going to try to do this live so that I can have some sense of the chat. And then it should also be recorded. And if it's recorded, then you guys will be able to play back later. If for some reason it doesn't record, I'm also recording a local video, and that local video I'll upload to the YouTube channel. So I'll try to keep the chat up here. I'm going to pop it out so that I'll be able to hopefully keep tabs with you guys. And so just let me know if you guys have any trouble or any problem. And yes, so we'll go ahead and say welcome. Welcome to machine design and analysis. I'm really glad that that we get to start this semester. I'm going to try to see here if I can go ahead and make the presentation full. Looks like I'm in the wrong display settings. So I'm going to swap. All right. So it looks like the stream is being cut off a little bit. So I'm just going to go and see if I can't figure that out. Okay. All right. So I think doing the full screen for the slides is going to be a little problem. All right, let's see here. All right, excellent. Okay, well, I appreciate the feedback. All right, so this is our machine design class. It's actually a machine analysis and design. And So I'm just gonna go through the slides. These will be available on Canvas after I upload them. And we're just gonna walk through here. We're gonna do things a little bit different, and I'll explain those things here, okay? So question that we need to answer is, why are we here? So this is a required class, either this one, I think the thermal fluids design. We're here probably because either you couldn't get in the other sections, or you couldn't get into the thermal fluids class, or you're interested in the machine design or more classical mechanical engineering. And so the goal of this class is really to do both the analysis and the design. So when we talk about the machine analysis, that's the part of the course that really deals with how do we analyze the elements of machines. And a lot of other universities refer to this class, or some of the old timers will refer to this class as the elements class. So the elements class really is the, things like links, cams, gears, shafts, springs, bearings, fasteners, etc. So those are the elements. And so part of this class is going to be on understanding, how those things are designed the way that they are, how the elements are designed the way they are, and how do we pick those elements. And then the other part of it is, how do we use those elements to actually do design. Okay, so mechanical design and the machine part, the machine design part of it requires design. And I'm going to add here one of my screens so you can kind of see me as I go through this. I don't know if this will be helpful to you or not, but I'm going to try to. I don't know if it's beneficial for you to see me while I'm talking to you or not, but I'll put my little head down there so you can kind of have a face with it. All right, so what we're talking about is doing machine analysis. That's the elements. And then really the design. So in order to do design, you have to do design. So we have to learn by doing, and you really don't know what you don't know until you try to do something. My view of machine design is that we actually have to make good decisions. And for mechanical engineers and machines, most of those decisions involve real hardware, and that hardware is often those elements. Not only those elements, but like combinations of the elements. So if you think about a servo motor has bearings, has gearing, has gears, has shafts, and also can have speed reducers or what have you. So that's really like an element or a piece of hardware that has a number of different elements in there. Obviously in 14 weeks we don't have time to design all of the elements or go through all of the elements, but what I hope to accomplish is that you can make decent decisions in machine design through this class. So that's why we're here. I will hold office hours, and I do appreciate the mention. I see Joshua Smith is nice, so you guys can feel free to comment while I'm talking. I'll kind of monitor those, and if you have any questions, feel free to post those up. But I'm going to do office hours on Google Meet. They'll be Monday and Wednesday, the same day as the class. And I will mention, I know that some of you were a little bit confused about this hybrid class. The hybrid class is we were supposed to meet half the class on Monday, and then the other half of the class would be online. The other half would meet on Wednesday, and then the other half would meet online on the same day. Since we're online till further notice, what we're going to do is use we'll just figure out a format that works, whether it's this studio and this broadcast or Google Meet. We're going to test that at the end of this lecture and make sure that we can all get on. But the plan is to hold office hours on class days from 1 to 2. So that gives us a little, like 2 hours before class. I don't intend to leave the Google Meet link up with my webcam just staring at me for an hour if no one is there. So I'd appreciate it if you email me. First, I'll probably give you guys a Calendly link that would allow you to pick a spot on my calendar for whatever is available. That way we don't have to go back and forth, and you can still get the help that you need with the plans. Yeah, so Zaid Fadel made a comment. He said the UNC website says we're meeting Monday only and Wednesday is TBA. That's just how they implemented the hybrid class. If you were in the other section, it would say you were only meeting on Wednesday, and then Monday is TBA. And TBA is just to be announced. That would be the web version. But since we are not meeting in person, we're only having a web meeting. It's scheduled during the normal class period, which no one should have classes scheduled on those other days. So you will be able, we should be able to meet there. And if you can't, for whatever reason, I'll record the lecture and make sure that you have access to it, so that if you can't make it during the class time for any reason, you can still have access to the lecture. The pace is going to be pretty fast though, so you can't get behind, and you can't just wait a week to watch the lectures, because there's no way you're going to be able to keep up. All right, so the textbook. So we're using the 6th edition of the book Machine Design, an Integrated Approach by Robert Norton. So it's a required textbook, so get that one or get an older version. If you do get an older version, it's your responsibility to make sure you are solving and turning in the right problems according to the syllabus. So I'll show you that, the syllabus and the schedule in a minute, and I'll upload that to Canvas today. When we do design, it's often what we're designing is connected to other parts of the design, and it's hard to keep track of that, or to see the effect of design changes of one element on the other elements. And so we're going to use Engineering Equation Solver. So have any of you guys used EES in any of your other classes? I'm going to see if you have used that. So EES, and I think there's a little bit of a lag between my questions and when they're received. No, so we have a no, another no, more no's. Okay, lots of no's. So they're often used in thermal and fluid. Okay, I get it. Everybody's a no. They're often used in thermal and fluid classes because of the connection between all the parameters. But for our case, since we're doing machine design, if we change the mass of a component and then find out later that we have to have a slightly larger motor, but like let's say we change the mass by 10%, and we work out all the rest of the equations, and it works out to say that we need a larger motor. Well, maybe we've already specified a 3 horsepower motor, and so that design change would put us over the design for that particular component, and then we'd have a problem. And so it's a little bit difficult to do all the bookkeeping, and it's difficult to keep track of everything. It's real easy to make a mistake, or for you to order a bunch of hardware and then realize your motor's too small, and then you only have like a week left until your deadline, but it took 2 weeks to get the motor in the first place, and you ordered the wrong one. So that kind of stuff happens quite often. So EES is a way of capturing your design in software and equations, so you can see the relationship between masses and torques, and then masses and deflection and things like that. So I'll give you some information on that. I might record a separate lecture or have a little tutorial at the end of one of our classes where you can get an overview of how to use Engineering Equation Solver, or EES. I've already been talking to the IT department, and you should be able to use VPN, log into campus, and yeah, so yeah, that's the wrong book. So we got a question from Kyle that says that's the juvenile book, and the correct book is Norton Machine Design. And I'm using the 6th edition. Earlier editions likely okay. And I think the main difference is the video links, and I've given you the links to the PDF for all the videos. I've uploaded it to Canvas. So if there's any other questions, feel free to shoot them there. I'm sorry if you bought the wrong book. So I don't know what you mean by rip $50, but yeah, textbook prices are not a popular topic for anybody, even the authors. All right, so this semester we will do a course project. I know doing team projects is not the top of everybody's list of favorite things to do, but it does represent how most projects are done. When you need more people to help get things done in a reasonable amount of time, it is difficult to get all the work done yourself. And so we will be doing a course project, and the motivation here is design is what you have to do in order to learn design. And so we can't really learn to do design without doing design. And the reason for that is you really don't know what you don't know until you try to put everything together and try to make real decisions. And then you realize, well, I don't know how big this component should be. I don't know what to order. I don't know where to find this or that object. And so the intent here is to do an actual design project, which I'll describe in a minute. And by doing that project, you guys should gain a sense of confidence of what it takes to do design, and also be aware of what you know and what you don't know, so that you can make decisions early, make good decisions early. So for us to just study the elements like springs and gears and shafts and flywheels and whatnot doesn't really help you design stuff. So you may understand how these components work and how they're analyzed, but if you really want to do machine design, you have to do machine design. So as such, in this class, you will do a design project with some of your peers on a real problem from a company that actually implemented this solution. Okay, so let's talk about that. So our design project for this semester is a rotating mold cavity problem. And so I don't know how familiar you are, but with injection molding, you have some pellets, and these pellets are fed into a screw, I think it's Archimedes screw, and as the screw rotates, it heats up and pulverizes the plastic and forces it through smaller and smaller area, which increases the friction, which heats it up and causes it to be molten. And then you have a hydraulic ram at the bottom of the back of the screw, and it pushes the screw forward, which pushes plastic into the mold. And the mold has two halves. It has a core and a cavity, and the core is sort of like the outline of the part you want, and the cavity is the blank where the plastic will fill up. And then there's a pretty high pressure. So if you look here, this design, you don't really see the hydraulic rams, but there's usually these huge hydraulic rams, and the presses are designed such that they're indicated in their tonnage. Okay, And so you might have like a 50 to 75, 150, 200, 300 ton press. You're getting pretty up there when you're in over 200 tons, but you can have a 200 ton press, and the pressure just has to be high enough such that when you inject the plastic into the cavity of the mold, that it doesn't come out of the sides or push the mold out. So you have to have really high clamping forces, and then you will inject the plastic. Now, for our problem that you're going to work on this semester is there is a company that has a single shot mold machine, and they want to make it a 2-shot mold machine, but they don't want to buy another machine. And so they have to take this mold here, and if you look at that mold, that would be the cavity side of the mold right here, and they want to pick 2 different types of cores. So this would be the core for the first shot, and then you'd have the core for the second shot. And then let me show that here. So the question is, can you guys design a machine, and you will design a machine that will retrofit an existing machine that will spin this mold by 180 degrees and make a 2-shot process. So it turns out that this was for an older machine. They actually have commercial machines available now, and I'm going to show you what that looks like here. So this is a company. This company is Hansen Plastics, and Hansen Plastics makes these 2-shot machines. So that's the core. So here you have the 2 cores on the mold. So this is the first one. You're going to have a shot that goes in here, and then the mold is going to rotate over to here, and then you'll do the second shot. Okay, and this guy, I have the link in there. This guy's explaining that that's the first shot. So the first shot is the structure. That's the ABS plastic here. And then the second shot is this TPE, which is thermoplastic elastomer. It's just used as a gasket material. And this is actually for, I believe, a fire alarm or fire extinguisher or smoke detector housing. And so by doing this, they can actually get the first shot of the ABS and the second shot of the gasket material all in one process. Okay, so you can kind of see what they're doing there. And I'll see if we can go. You can see the machine go back and forth. So now you can also see it injects it. It opens, it'll flip around. Okay, so that part right there is what you're going to design. So you're going to design a machine in this class with your peers that will spin that mold. Okay, so you're going to have to design the shaft. You're going to have to design it against deflection. You're going to have to design the bolts and the fasteners and whatever else needs to be part of that. They actually have another example in that same video later on. They have a larger machine as well. So this is a 275 ton press. You can see that right here. So it'll spin, it'll shoot out that part when it's done, and it'll do the 2-shot mold as well. Okay. So obviously you can kind of see this you can't see, but there's gasket material here. And then as they rotate that thing, as they close it up, it has gasket material that'll clamp onto what it's trying to clamp on. So that's pretty cool. All right. So yeah, those machines are expensive. All right. So instead of just insisting that we arbitrarily assign teams, we're going to have actually 15 teams of 4 students. There's 56 students in the class. There were 60, but I think when I sent the email saying that there was going to be a design project, I think maybe some people bailed. I'm not sure what we have 56 now. So we'll have 15 teams of 4 students ish. There'll be, I guess, 4 teams that only have 3 students. And you'll have until midnight tomorrow to pick your team members if you want. So I'll wait until tomorrow midnight, and then Wednesday morning, if there's no teams assigned, then I'll pick that. So there are some potentially helpful suggestions that I have. So if you can find some partners with compatible schedules who have time to meet and work together, then that'll give you a greater chance of success if you can actually schedule time. So one of the things you might ask somebody if you're picking your partners is, hey, are you on campus? Are you in North Carolina? When are you available, etc. So you basic things. Also, it may not be the best thing for you to pick your friends because you may not be friends at the end of the semester if people don't do their work. And it may be a good opportunity to meet some new people. So you're welcome to identify your partners. I know some of you guys know each other and would like to work together. That's fine. If you do, you have until midnight tomorrow to pick your team. If you don't, I will go ahead and assign the team so that we can get started. We don't really have enough time to fiddle around with this, and it's not going to be such a hard project where you can't, finish it. We have plenty of time and should have more than enough people to get it done. Yes, there's 2 sections, so you can work with people outside your section because we're meeting online anyway. And if we do go back to on-campus meetings, then we can have those members like log in virtually or whatever. So I don't care if you meet with people outside your section. I also think that I just sent the email that had everybody's email address on there. So you should have everybody else's email that's in the class. I don't know if there's another way. Is there another way for you guys to see if there's people? Can you see other class members? So Max asked if we could intentionally choose only 3 people. You can, but if I need to assign a 4th, I may add a 4th to your person. In the form that I sent, I did send it out where there were 3 people that were required in the form, but and that 4th one was not required. But in the event that I get a bunch of 3-person teams, I'm still only going to have 15 teams. So all teams will have four people except for 4 teams. So I don't care if you're one of those, that's fine. Okay, so on the people tab, you can see all the people in the class. Thanks, Jeffrey. So I'll try to accommodate what you would like to do with as far as the people. I mean, picking your own people. But if you don't have anybody, I will go ahead and assign those. I already said that. So moving on. All right. So do you think that we will be back to class? I have no idea. I'm happy to. Yeah, I have no idea. All right. So I want to walk you through some of the report guidelines. Okay. So there's about 60 people total. So if you go to Y03 and Y04, Jeffrey Cecil says there should be about 60 people. So if you see 60 people, I think the sections in Canvas are merged. Not 100% sure. I appreciate you checking on that. Usually you get in trouble when you're on your computer in class, but I guess not now. So yeah, get on Canvas. Tell us what's what. All right. So report guidelines. All right. So this is going to look a little bit frustrating at first, but really it's all you have to do is copy the template and then fill it out. And I've tried to give you enough information so that it's really easy and straightforward. You shouldn't have any trouble. you really shouldn't have any trouble following the directions, okay? So I expect you to follow the design process that's outlined in the first chapter of the book, okay? And so this is the first chapter, which is fundamentals. And if you go through here, you see that there's the introduction of design. If you don't have a good sense of it, this is part of your assigned reading anyway. And if you just look, there's the deed, the goal, the background. It pretty much walks you through what I expect to see in the report. And again, you have 14 weeks to turn this in, but you should be able to put this together. So that's what I expect. These are the pretty standard phases of design. You basically have concept, ideation, and then you go into detailed. So this is often called concept design, and then embodiment design, where you start to put real numbers and sizes and dimensions, and you go to detailed design and documentation. Okay. All right, so there's some examples and some reporting and some other stuff that you can use, and it pretty much walks you through that. So if you look at what I'm asking you to do, this is just, a report format, and then you can read through this. You're going to have to identify a project lead, but I expect everybody to read through it. And then I've broken it out to where you can see what's required and the length of the number of pages. Okay, so this is kind of what I expect in terms of the reporting and the effort. If you think about it, and you got 3 people, on your team, then it means that over the course of 14 weeks, each person only has to generate 10 pages worth of content. And those include pictures and graphs. So it would be a lot of work if you try to get it done by tomorrow. It's not a lot of work if you just follow the process. Okay, and I'm going to walk you through the process in the class, so that filling these things out should be relatively straightforward. Okay, and then I have this broken out where you can see, exactly kind of what each thing is supposed to be, and it should be like pretty straightforward. Now, as long as we're designing a machine that people care about, and you have a well-defined problem, and you can go through the process and you have enough information, it shouldn't be super frustrating. And my goal is not to judge you on how well you can make a report, but my goal is to get you to actually be a skilled mechanical engineer that can write a basic report on a design that they did over 14 weeks with 3 other people that should have taken them about a week to do if they're a practicing engineer. Okay, so this cover, paper, arranging, and whatever you have. So I'll upload this, and you'll be able to look at it in more detail. So are there any questions about that? I'm sure we have some questions about grading, so we'll get right into that. Okay, so this is our syllabus, and I'll upload this. I've already said this is the text. It's different than what the bookstore recommends, but you don't really want to buy books from the bookstore anyway, because they charge you like an extra $100. Okay. There are a few other useful texts, and I highly recommend that you build your library. And as part of building your library, these are some books that I'd recommend that you take a look at. One is Shigley's, which you probably have if you've taken one of the earlier design classes. And then there's the Juvenal and Marshek book. There's actually a 6th edition available now, which would probably be a different ISBN, which I'll have to fix later. And then there's a book by Schmid, who's a professor here. Actually, he was formerly at Notre Dame, and then the National Science Program Manager. And he recently came here to UNC Charlotte, and he's written a book on the fundamentals of machine elements. So you see, this is machine elements, this is machine components, and then we're using machine design, but it's really, some people call it the elements class because it's the component design. All right, so the time and place. Until things change, we're going to meet from 4 to 5 using whatever format you guys prefer. So we're trying to do this via streaming so we can have some sense of back and forth and collaboration and live class instead of just, watching a recorded video. And then we'll have office hours. So my office is in Duke on the first floor and 164. This is my email address. I have a TA, Chunji Fan. He is going to hold office hours Friday, 9 to 11. He's going to send a Google Meeting link. He's actually on here, should be on the chat. We'll see. Chunji, if you're there, let us know. Say hello to everybody. And then I'll make myself available. And I have a Google Meeting link. So you can just email me and I'll be at this link right here. It should be live. But if not, then I guess we'll find out. Yes, the document will be uploaded to Canvas. Everything will be uploaded. Yes, so you don't have to pay super close attention, but yeah, you'll be able to find the links. Hey, there's Chunji. He goes by Steve Fan, so he says hello. So Chunji, if you can send a link out for your meeting on Friday, or invite me, and then I'll invite the rest of the class so that they'll have the Google Meet link. And we're going to test that here in just a minute. All right. So this is the course information. So the first part of the course starting Wednesday is a review. Prerequisite for this class is statics and mechanics of materials. You should have remembered this stuff. You should have. So Robert is excited to see Chunji. Ryan is excited to see Chunji. So we'll do a review of the different stress components: normal, shear, principal stresses and strains. Moore's circle, which is basically how we find the greatest stress and what the orientation is. We'll look at different stress distributions under axial loading, bending, and we'll look at deflections using. Okay, I have the link. I'll send that out. We'll look at deflections using singularity functions. We'll look at the mechanical failure mechanisms, which is for brittle and ductile materials. We'll look at fracture and fatigue, and look at the different failure theories that are used to describe a failure. But at the end of the day, when we design something, we have to know what the forces are. And so we have static and dynamic forces, and we have to resolve those forces into find the places on the components where the forces are the max, and then relate those to the failure criteria. So we'll do that. And then we'll get into the elements. We'll get into shafts, contact, stresses, surface failure, spur gears, springs, bearings, and lubrication, and then some power fasteners, riveting, welding, and bonding. So ideally, I will be in front of your design process with the lecture content so that you will be able to use the information that we've lectured on to do the design or add detail to the design. It's really difficult for this to line up perfectly, and so you may have to be a little bit willing to maybe go a little bit ahead, or the schedule may not lend itself perfectly to the content being covered before you have to generate something for the report. But in general, I will try to cover that ahead of time. In the event that we don't have all the information for the report that's due, then we'll just do the best you can, and then we can go back and add detail. And as you can see, the grading on the report is a little bit light in the beginning, and it's mainly at the end. So you can kind of work your way through the design without having to have everything perfect. But I'm pretty sure by the end of the semester, it'll come out nicely. All right. So these are the course outcomes. Essentially, my desired course outcome for you guys is that design would be a process that you're comfortable with, and you could move quickly through components to solve machine problems for the basic elements. And I think the project that we have for the semester will make that a little bit easy for you. All right, so for the grades. So in this class, we'll have 4 exams, and we'll have a semester project, homework, and then design review and reports. That's 5%. So the grades on Canvas may not accurately represent the weighting. I'll try to put them in Canvas properly so that your grade is reflected, but just make sure that, like, we're going to go off the syllabus. And so you can calculate and keep track of your own grade this way. I reserve the right to play around with grades by plus or minus 2%. Homework, you got to use your units. Your homework needs to be neat. I'm well aware of all of the many different forms that you can find answers to homework problems. I still expect you to turn it in, and you'll get a grade of 1 to 5. So 1 is you put your name on the front and wrote down the beginning of the problem. 5 is, it's neat and you got the right answer and it looks like you did all your own work. All right, there'll be a total of 4 tests. How we're going to administer the test, I'll probably email you a PDF. We'll have to figure out a little bit what to do. There's been some problems with people that want to all work together on their tests, but I think we're going to time box it and basically make a PDF available. You'll work it and then upload it and then be done. There won't be any makeup exams, so you'll need to be able to schedule a time where you can do it if you have some extenuating circumstances. Okay. The final project. The final project is going to be 30% of your grade. So if you do everything else perfectly and you bomb the project, you can still get a C in the class, which in my opinion is just the average grade. So, but really expect you to do well on the project. I expect everybody to get full marks on the project because we have more than enough time to get it done. Office hours, which I've mentioned, 1 to 2 Monday, Wednesday. Here's the link. Chuji also has office hours on Friday morning. Academic integrity. There's been a lot of violations when we went online last semester. People getting other people to solve their problems on Chegg and people copying other people's solutions. So just going to say that when you do that, or particularly when you're learning technical content, if you get help from other people, you can't wire you prevent your brain from making the connections that it needs for you to actually do the design yourself. And so I strongly encourage you to struggle through that. Start early enough so that you can get some help. A lot of the answers, a lot of the problems that have been assigned actually have answers in the book. This is the 6th edition of the book, so most of the errors are gone. So you should be able to work through those problems yourself. I know that being online and being away for some people is pretty challenging and can get a little bit overwhelming, and that a lot of times it is easier to be around other people and work with other people. So I do encourage you guys to collaborate, but you can't cheat, and just please pay attention to that. All right, so this is what our schedule is going to look like. All right, so pay attention here. This is a kind of a This is pretty important. As you can see, we don't have much time to waste. So are there any questions so far? Now I'm not sure exactly what the lag is here between when I post stuff and when you get it. So I don't know if people are still with me or not, so we're just going to keep on moving on. All right, so this is our schedule. And so here we are, this is the first day of class. And we're going through, and we have an assigned reading. So you really need to be reading the book, read chapters 1 through 3. And then come Wednesday, we're going to start right in with okay, no questions. Okay. All right. So we're starting with chapter 4, which is going to go over the normal and principal shear stresses. And so the first, okay. So I'll answer that with the due dates. So the first homework is going to be due 2 weeks from today, and it's all previous homeworks due. Okay. And it's the same day that we have the test. And so between now and next Monday, and so our first test is going to be 2 weeks from today, which is September 21st. And it's going to go through all previous Wednesday's classes. So this is what the first test is going to be over. And then this is the first homework. So I'll get into that. So we have a question about the due dates and the final exam. So all previous homework due, which means that on Monday we have our first test and all the homework is due. Yes. So if you'll see here, we have our first test on September 21st. Okay, that's in 2 weeks from today. And then every 2 weeks we have either a design review or another test. Okay, and every 2 weeks, all the homework is due from the previous 2 weeks. Okay, so we have 1, 2, 3, 4, 5, 6, 7 homeworks that are due. There's only 8 problems in the first homework, I think. We got 1, 2, 3, 4, 5, 6, 7, 8. And so the idea is you're going to use the homework and to study for the content, and then you'll be ready to turn it in and turn the test in. My experience is that most of the students have access to the solutions for most of the books. And so for us to grade and turn back homework is not a super good use of anybody's time because the process is a little bit been hacked. But we still are available in our office hours to go over the homework and take a look at that. Okay. Thanks for that feedback. All right. So if you have any questions about that, let me know. So we're going to go basically in the first month is really, the first 2 weeks of the class is really a review. Okay. So the first homework should be on stuff that you've already had before. And the test will be something very, very similar to the homework. So then we're going to go into failure theories and have those homeworks due, and then fatigue, and then have that homework due. Okay, so the homework is due on, so every other Monday you either have a test or a design review, and you have a homework due. Okay, so that's how we're going to move through the semester, and it should allow everybody to sort of keep up with the rhythm of the class. Okay, so I think we have 28 or 29 class periods, and hopefully we'll go through the review material necessary to do the static analysis. We'll go through the different failure theories and fatigue. And then we'll go through shafts, wear, gears, springs, bearings, power screws, fasteners, rivets, welding, and bonding. And if we have time, we'll go in through to some other topics. On the design review days, what we will do is we will all log in, and this will be probably through Google Meet. I'll give you details. And when we log in, I'm going to randomly choose a team. So you will not know if you're presenting. You will not know if you're presenting until that day. Okay. So we have 60 students in the class. And so we have 5 teams presenting on October 5th, November 2nd, and then November 30th. So it's 4 weeks between each design review, and you actually have 4 weeks before the first design review. So you have a whole month, but you don't really have time not to get started. Okay. So, are there any questions about that? And I don't have any final on here. There is a final scheduled. Is there a dress code for the design reviews? No, there's no dress code. I don't care what you wear. I think we're all engineers and we're trying to do the engineering. Not necessarily going to judge you on all that professionalism. I care that you follow the right design process to design a machine. I could care less what you look like or what you're wearing. Obviously within the constraints of what is normal, but I think if you're as comfortable as possible and you're just presenting great work, I think everybody will benefit from it. Everybody is going to be required to go to the design reviews, because I want other teams to review other teams' design, and it's also very important for you to understand how other people are doing their work and understanding the problem. So how do you envision seeing us presenting? So I think you guys are going to use Google Meet, and you'll present your screen. And then your team of 4 people will go through your slides, and I'll give you some guidelines for that as well. Essentially, this is going to kind of follow what you would experience in practice if you had a design project on a team. You would be expected to update all the stakeholders at some regular intervals, and so we're just modeling that here. And so I'll randomly pick everybody, and obviously once we pick the first 5 teams, they won't be picked necessarily to present in the second and third meeting. So the third meeting, I guess all 5 teams will know who they are, but for the first 2 meetings, they won't know. If I find that people are not prepared, though, I might mix that up. So the homework has been designed to reinforce the lectures, and the class is designed to help you get to where you can actually design a real system. So I spent some time trying to make this reflect what I think will be the most beneficial to you. I hope that you will follow the process, and that you will, at the end of the class, be able to look back and say that you got out of it what you had hoped to get out of it. For the group, do each one need to fill in? No, just one form per group. So the question is, does everybody need to fill out the form for the teaming assignments that's in this link? And the answer is no. And I'll go ahead, I can post that here. You don't need to, and I'll go ahead and post. This is the design. That's the link to the YouTube, and I'll upload these as well. All right. So if you're in senior design, you know that an approach is followed. It's similar to waterfall design or Gantt chart design, where you try to predict the future. Problem with that approach is it's very difficult to predict the future accurately. It's very useful to go through the process of planning out the entire schedule, but it is very difficult to plan the future. And so what I'm going to have every team do is you're going to use Scrum, and I've created a template that you can use here. Okay, and I'm going to make this public and then reload it. All right, and I'm going to put that in your chat. And I'll also put the link in the presentation. So there's the all right. So there's the link, and so I'm going to just walk you through this quickly. There's some resources there. Okay, and so this is a way of managing the process, or managing the project. It will make your life easier, and it will make the work transparent, and it should make the job of the team lead a lot simpler, and no one should have to be reminded what they need to do, because everybody kind of knows what they need to do. But this is the process that you're in right now. You're going to make your team. You're going to come up with your design requirements for your process, and you're going to populate your Scrum board. And this is your Scrum board right here. Okay, and I'll walk you through that in just a second. So the first thing you're going to do is get all of your design requirements that are going to be mapped out into specific deliverables. And that's going to go into your product backlog. In this case, your product is a turntable for a die cavity for a 2-shot mold machine to upgrade it from a 1-shot mold machine to a 2-shot mold machine. Everything will seem a little bit overwhelming at first, but I think once you get into the details and you start to break it down, it'll remove some of that fear, and you'll actually break it down into tasks that can be knocked out. And that's the process that you're going to do here, is go to the product backlog grooming, and that's basically where you kind of look at all the tasks that need to be done, and you kind of sort them out, and you kind of plan them out into a sprint. And a sprint is basically where everybody works together to accomplish the tasks that they've set up in 2 to 4 week cycles. You have just about the ideal team size. The ideal team size is 4 to 5, and you have 4 people on your teams. And what you'll do is you'll plan your sprint, which will involve a sprint backlog, which I'll show you in a second, and tasks. And then you'll kind of meet together, and you'll complete work, update your board, and then you'll review at the end of every 2 weeks and see how you did. So this review process will kind of be in our nominal design process. We'll have that once a month, but I encourage you to review once a week. I've worked with David Ullman, who is the author of the Mechanical Design Process. I worked with him on this graphic and helped review it for him. There's a couple links to the 12 steps to organize it. So this is how you could organize the task. So there's some detail here that will be useful to you, and then you can update it. And then there's the graphic, and you can find some more information on his machine design process website. Scrum is comes from scrummage, which is a rugby term, and it's when everyone pulls together. Then that's the idea of Scrum. And so what it'll look like for you guys is you have a product backlog, which will essentially be, design a turntable to rotate a die to upgrade a single shot machine to a 2-shot machine. Okay, so then automatically you get tasks that are going to be associated with this task there. And so that's the product backlog. So what do you have to do to do that? Oh, well, we need to determine the mass of the die. Find out what the acceleration of the die is. Determine the loads due to those dynamics. Design a structure that can't spell here, that meets deflection requirements. Okay, and you can see like you have a big task here, but then you have to do all this other tasks. So that's the process that you guys got to go through to take that big task and then break it up into little tasks. And then what you can do is you can add a person for your own board. There's only me on this board, but you can create a board. I think you can create a free board for UNCC, and then you can add your team, and then you can label and do checklists and due dates. And so it's pretty useful. You may want to have some other stuff, such as take the Myers-Briggs test and pick the team member with the best planning skills / personality to manage tasks. You can take it at 16personalities.com. Something like that. All right, you get the picture. All right, so we also have the project specs, and then we have the project itself. So this is a write-up of the project for the 2-shot ABS. So we want to create this turntable here. There's some more information here. It has to be 180 degrees rotation. It's got to go back and forth. It has to do that travel in 0.8 seconds. That tells you what the acceleration needs to be. We'll talk about that stuff. It needs to operate 24 hours a day, 7 days a week, 50 weeks a year, and no failure is allowed for at least 10 years. So that'll get into your fatigue failure. When it's mounted, you can't have 1/1000th of an inch deflection, either in the vertical, which would be in this direction, or the axial direction, which would be due to bending. Okay, so you have to take a look at where the center of gravity is and how that'll pull off and all that stuff. You have to use a computer software to solve the problems. For example, when you design the different components, you're going to have stress calculations for different masses, and you need to basically have that automatically calculate with the software program. This is the schedule and kind of where I expect you to be at each phase of the design. You already have taken statics and mechanics of materials. You should be able to define the statics of the problem based upon this mass of the mechanism, and you can just assume it's steel, and this is the volume. So you have the density times the volume gives you the mass, and you can use the mass for steel and start to do some of that stuff. You have 4 weeks from today to finish the first phase of the design, and then you'll have the second phase of the design, and then the third phase in your final project. So if there's any questions about that, let me know. And there's one more thing that we have to do before we go today, and that is I would like for us to take a look at the YouTube channel. Okay, so this is the YouTube channel here that has the playlist for machine design from last semester. I will tell you right now that these videos are way too long and too slow because I'm trying to look at a screen and read my notes and write on a tablet, and they're painful, and I'm sorry about that. But there is good information here and information that might be useful to you, and it's all available to you on the YouTube channel. All right, so the next thing I want to do is I would like for you all to please click on this link now, and we're going to jump over to a Google Meet. Okay, so please click on that link, and I'm going to open that up, and I want to see if we can all get in. And at this point, we'll see if we can get in. I'm going to go ahead and stop this recording. I see some people already in. I'm going to stop it, and then we'll answer questions in the Google Meet.